So welcome to Tejano Virtual Events. We have a great presentation for you today. Today we have Mr. Tintos, who is one of our EPCC math instructors, and he's going to be helping you prep for finals with a final exam review. So for attending today's workshop, you have the opportunity to earn Tejano Passport points. So during the workshop, I'm going to be placing that code in the chat so you can get points for attending today. And I'll share more about this program after the workshop. So please get comfortable, mute your mics, and if you have any questions, please raise your hand or place them in the chat box. And so now I'm going to turn it over to Mr. Tintos.
Good afternoon, everybody. Thank you for joining us. Let me just share my screen and then I'll begin the presentation. Okay, let me check my mic very quickly to see what my sound is. I think it's fine. All right, so this is, let me get started. So, welcome to our Calculus 1 final exam review. The agenda for the day is I want to cover like topics that are very common in calculus that probably will be on your final exam. I would maybe one might not be, but all of the rest, which is limits, continuity, derivatives, implicit differentiation, related rates, optimization, Riemann sums, and integrals. And just very quickly before I get started, I did wanted to say that calculus has a lot of applications. We use it almost every time when there's an object moving, and the whole world is always moving. So calculus is actually much more appropriate to model any phenomena rather than using like regular algebraic equations. So some of the applications would be seen in the related rates optimization, but there's more, even more. So maybe at the end of the presentation, I can discuss some of the other applications. Okay, so the first one is going back to the limit. This is the first thing that we probably study in the course. And basically, a limit it's supposed to tell you what is happening when x gets closer and closer to a particular number. And on the table below, what you see is the difference between evaluating a value. So when you plug in a number into a function, what you're kind of asking is what is the value of the function at that specific number? What is the y value when you input x2? In the limit is asking about what is the function approaching when x gets closer to 2. So in fact, not always these two are equal. So that's kind of like the difference. In here, it's asking like for that specific value when x is 2. And on the limit, I always like to say like everything that happens before and after. Okay. So as a way of an example, I do have, so this is kind of like a typical question. You would be given a graph and then you have to find the limits based on the graph. Well, I included here not just the limit, I included one of the values. So for A, I gotta find the value of the function when x is -8. And on my graph, -8 is right here. And actually, the value is the full dot or the full circle. So the answer would be -3. Let me see if I can write it. So the answer would be -3. For part B, now what is the limit of f of x when x approaches -8? So now the question is, what is the function approaching when x gets closer to -8? Well, notice that the function is actually below. And when I approach -8 from the right, then the graph is actually going to that open circle. And if I approach from the left, then the graph is actually going to that open circle. And so the limit would be like what exactly that point, the y coordinate of that point, which is -6. So you could see this is one of those examples where they're different. So in fact, the limit does not even care about what happens at that point, at -8. So even if there was not a full circle, the limit would still exist because the graph before and after is approaching that value. Okay, another example would be, what is the limit when x approaches 6? So now 6, positive 6 on the graph is here. And we could see that from the left, the graph is approaching a height of 2, but from the right, the graph is approaching a height of 5. So these are two different values, which means this is an example where the limit does not exist. So these type of limits, there we call them like two-sided. So both sides need to agree, like we saw in -8. So if we have on the left and on the right different y values, then the limit does not exist, which we abbreviate by DNE. In letter D, now it's asking me, notice that there's a negative, but it's in the exponent location. So this wouldn't, it doesn't mean -6. When you have that negative on that position, it's actually from the left. So this is a one-sided limit. When you see those signs, negative or positive, these are one-sided limits. So this is the limit when f approaches 6 from the left. So from the left, the answer is 2. So this limit doesn't care about what happens on the right. It's just on the left. And then let me now notice that I also did a limit from the right. So from the right, that would be, the number would be 5. So I would put a 5 right here. So the two-sided limit does not exist. But if you ask from the left and from the right, by adding those signs, the negative and the positive, those limits do exist. Now, f, one more time, is just one value. What is the value of the function when x equals 6? Well, the value when x equals 6, the correct value is where the solid dot is, which is 5, not the open circle. And if there's not solid dot, not a full dot, then you're supposed to put that is undefined, meaning that there's no value for 6. The next one is letter G, and this is the limit of the function when x approaches -2, and then we have from the left. So -2 is here. From the left, the graph is going to 3. So this limit is +3. And last, the limit when x approaches -2 from the right. Well, from the right, if you guys notice, on the right of -2, the graph seems to be keep on going up and up. So that means that it just goes to infinity. And so we often write the infinity symbol. So that limit is infinite. Writing infinity, it doesn't mean that the limit exists, because there it's not a number. So what it means is just the graph keeps on going higher and higher without a bound. So kind of like infinity is your bound, which means there's no bound. You could go as high as you want. Okay, so now that's usually finding the limit from a graph, but often we also find limits just by giving you the function and the whole limit. So one of the strategies to finding limits without using the graph, if you don't have the graph, then it is using direct substitution. This is the easiest one. So the question is, find the limit when x approaches 1 of x cubed plus 2x minus 1. Well, literally, substitution means substitute the x with 1. So you plug in the 1, and the answer is 2, which means the limit is 2. So often it is as easy as that. And I always recommend start always with substitution. And if it doesn't work, then you try something else. So that's kind of like the first technique that you want to use. The second one is factoring. So in this example, we are asked to find the limit of a rational function. And rational means that there's a fraction. So we have x squared plus x minus 6 over x minus 2. Now, right away, you might notice there is a problem when x approaches 2, because if you were to plug in 2, what happens is that on the top, there's no issue. You get 4 plus 2 minus 6, which in fact is actually 0. But when you substitute in the denominator, 2 minus 2 gives you 0. And The 0 on the top is not a big deal, but the 0 on the bottom, it's a big deal because in math, we don't divide by 0. So this is what we call undefined. So this function, this fraction does not have a value. So if I were to do the graph, I would see one of those holes that I saw in the graph that we saw in the previous example. So instead of using substitution, then we want to kind of like simplify it before we substitute. Well, since we have a quadratic equation on the top, we can factor it. That's why factoring comes to mind. And since it is x squared plus x minus 6, we're looking for two numbers that when you multiply them, it gives you the last one, the constant. And when you add them, it has to give you the middle term. Let me put it here. We don't see a number, but because we don't see a number, it's a 1. And the two numbers would be positive 3 and negative 2, because if you multiply them, you get negative 6. And if you add them, you get 1. So this would be this would be the factorization, x plus 3 parentheses x minus 2. So substitute the entire quadratic equation by the two factors. And you probably already noticed that x minus 2 matches. We have it on the top of the fraction and on the bottom of the fraction. So these are common factors, so we can cancel them out, and you get only x plus 3. Since the whole x minus 2 cancel, there is no longer a fraction, so my limit is simply the limit of x plus 3 when x approaches 2. And here I can do substitution. I plug in the 2 and I get a 5. So the whole limit is actually 5. I don't think I put a conclusion, but so I'll put it here. So my final answer is 5. The reason why this works, even though it may seem strange, is that since the limit does not depend on the value, the function is not defined at that value when x is 2. But if you simplify it, then you can actually, you find that the entire graph is simply a line that has like an open circle. So it goes something like this. And so even though the value does not exist at 2, the limit is actually 5. The height is 5. Okay, so let's look at the next technique. Another type of problems usually have a square roots, and the technique, I call it the conjugate method. Some people may call it rationalizing or rationalization. But I just prefer to call it conjugate. So when you have a square root, you can find what we call the conjugate. And let me start by mentioning it. So in general, if you have a plus b, the conjugate would be a minus b. So we're going to use that in this problem. So the first step is to multiply by the conjugate. So if I look at the entire square root, it's the entire numerator. This is the square root of x plus 2 minus 3. So this is the whole square root is a and b is 3. So I switch the sign on the second one, which would be plus 3 instead of negative 3 plus 3. So if I had, let's say, 1 minus 2x, the conjugate of this would be 1 plus 2x. So always the first term stays the same. The second one is the one that changes sign. So here, all of this is the first one, all of this is A, and this is B. Very important that you don't switch the sign inside the square root, because if you switch it there, then you'll get the wrong final answer. So once you have the conjugate, since this is a fraction, you multiply by the conjugate on the top and the bottom. And the nice thing about conjugates is that we have this formula, which some people call the conjugate square formula. And sometimes it's called the difference of a squares formula. But we're looking at it kind of like in reverse order, because I have this multiplication. So this would be my a minus b multiplied by a plus b. And so according to the formula, you just got to square a minus the square of b. But since I have a square root, since a is the square root of x plus 2. When I square that, then the square root cancels with the 2, and I get x plus 2, which is this. And the square of b would be 3 squared, which is 9. And so I get x plus 2 minus 9. So by multiplying by the conjugate, I cancel the square root on the numerator. On the denominator, I didn't really multiply. So it was all of this multiplied by x minus 7. And if you notice, I just left it there, expressed as a multiplication. I don't need to multiply them because if I simplify the 2 minus 9, this becomes negative 7. And I'll have x minus 7, which I can cancel with the x minus 7 below. So that's the strategy. Notice that once I simplify these two, I get x minus 7, so I can cancel the x minus 7s. And I get a 1 over square root of x plus 2 plus 3. At this point, I substitute the 7, and it gives me 7 plus 2, which is 9. The square root of 9 is 3. 3 plus 3 is 6. So my final answer is 1 over 6. Now, when I started the question, I did not even try to substitute the 7 directly into the original fraction. But if you do, you will realize that you get undefined as well. So you get 0 divided by 0, which means you got to try something else. You cannot just substitute here. And the way that you can simplify that fraction is by multiplying by the conjugate. Anytime that you multiply by the conjugate, the square root cancels on one of the sides, either on the numerator or on the denominator. Okay, so let's do another example. I think this is the last technique. So sometimes we have fractions, and this is a very important fraction. It's called the difference quotient. And when we want to find limits that have fractions, my indication is always like try to do a little bit of algebra, like simplify. What would be something that we could do of algebra? Well, I have two fractions on the numerator. I could simplify them by getting the common denominator. Or a simple formula that you can use is that you can multiply the two denominators, which is 5 times h, and then kind of like multiply in diagonal. So 2 times 5 would be 10 minus 2 times h plus 5, which is how I got that. That's kind of like a shortcut to combine the two fractions into one fraction. And of course, I could always like distribute this negative 2 in the parentheses and simplify even more. In fact, if I do that, I'll have negative 2h, and then negative 2 times 5 is negative 10. I can cancel my positive 10 with the negative 10. And it simplifies as negative 2h over 5h plus 5. Okay, so now I put the whole thing. So notice that initially I had a fraction and all of that was divided by h. So I simplify the numerator, which is all of this, and then my fraction divided by h. And when you divide fractions, you actually divide fractions by multiplying by the reciprocal. So I could make the h into a fraction itself. And so now I have a fraction divided by another fraction. Well, you keep the first one the same, keep it the same, and then flip the second one, which becomes 1 over h. When you flip it, you switch the order of whatever numbers or letters you have. And now instead of dividing, you multiply. And multiplication of fractions is pretty simple. It's just straight across. So you multiply negative 2 times 1 and 5 times h plus 5 times h. You multiply across, like straight across. And but in this case, before you even do that multiplication, you can actually cancel the h's since you have 1 on top and 1 on the bottom. So this is negative 2 times 1, which is negative 2, and then you get this. All right, then. Well, just like before, at the beginning, I couldn't plug in 0 because if you plug it in, you actually get 0 divided by 0. But once I've done all of these simplifications, I get this expression. And indeed, in this expression, I can actually plug in 0. And then if I do, then my limit is going to be 5 parentheses 0 plus 5, which is just 5, and 5 times 5 is 25. So my final answer is negative 2 over 25. So I'm pretty sure this is the last limit technique. This is just like a quick review of how to find limits when you don't have the graph. So we use like different algebraic operations or algebraic strategies to simplify. So it was the first one should be direct substitution. Try if you can substitute it, and that already gives you an answer. You could also try factoring when you have quadratics. If you have a square root, you use the conjugate method. And if you have fractions, you just want to simplify the fraction. So this is a very common one. If you have the difference quotient, you will have a fraction. And in fact, in the difference quotient, the key is that you want to cancel that h. So this is kind of like a trick or a tip. If you simplify, your simplification has to cancel that h at some point. If it doesn't cancel, then you probably miss one of your steps. Something went wrong because you want to cancel it so that you don't have a division by 0 anymore. And once you don't have it, you can just plug in 0 into the limit. Okay, so the next topic is continuous functions. Continuous functions are the basis of all of the operations that we do in calculus. In fact, when you don't have continuous functions, bad things happen. You got to do a lot of like extra math because the function behaves kind of weird. A continuous function is one that satisfies three conditions. And also continuity is something that is local. You're supposed to verify, and this is gonna sound kind of crazy. You're supposed to verify each number. So if you want to say that a function is continuous at one number, which we call a, you gotta verify three things. One of them is that the function is defined at that value. So if you look at a graph and you see a hole, then the graph is not continuous because it has to be defined. That was the first condition. The second one is that the limit exists. So even if it's not, well, besides being defined, the limit has to exist to the left and to the right. And we've seen that that is different from the value of the function at that point. And last, they actually need to agree. Whatever f of a is, whatever height it is at, it has to match where the function is going. So this is a very interesting definition. At first, it may not seem intuitive, but if you analyze it, this allows you to create functions. Any function that has these three conditions is a function that you could draw on one piece. So literally, it's like a continuous line or a continuous curve, I should say. So these are examples of continuous functions. Typically, these functions, we call them polynomials. So this is a polynomial. So it has a lot of like curves, up and down, maximum, minimums, and it usually goes to infinity or to negative infinity at the end points. But we also have other functions that are also continuous, such as the trigonometric functions. Remember that they're periodic, such as sine. Exponentials are also like it's a single piece. And even the logarithm function is continuous on its domain. While the first, the second, and the third example are continuous for all real numbers, the natural log and all logarithms are only defined for positive numbers. So you see that the graph is going down, down, down to infinity as it gets closer to the y-axis. So, but despite that behavior, the graph is continuous everywhere in its domain, in the values for which it makes sense. So we don't look in the negative values. Now, before I had this example when I did the limits, and this graph had all of the discontinuities. So one of them is We call it a removable discontinuity when the graph is not defined at a point. And this is, well, actually, it is defined at -8, but it doesn't match. So this graph is not continuous at -8 because the limit, the graph is approaching -6, but the value of the function is up here. So that's a removable discontinuity. And basically what you would see is that there's a hole in there in the graph. Another type of discontinuity, we call it a jump discontinuity. And we saw that at 6 because from the left, the graph has a height of 2, but then from the right, the graph has a height of 5. So it's not matching the value, so it creates kind of a jump. It goes from here and then it jumps all the way till 5 and continues through there. So again, that type of discontinuity is called a jump discontinuity. And last, the infinite discontinuity, this occurs when the graph literally goes to infinity or negative infinity. And we saw that at -2. Notice that it doesn't matter if it's not both sides, because from the left, the graph is going to 3. But from the right, the graph is just going to infinity. So this is classified as a infinite discontinuity. Okay, so that was just like a quick review of continuity, as it kind of like plays and well, not kind of, but it plays an important role in all of the theory of calculus. So often we're like dealing with continuous functions because these are kind of like the better behaved. But there are such things as discontinuous functions, and they're a little bit more complicated for everything. Even just to find derivatives, often the derivative does not exist when there is discontinuities. Uh, so the next topic is actually the derivative, and this is the definition. We call it the limit definition of the derivative. It's actually not the only one. It involves the different quotient. The other definition of the derivative is that you could also find it. So if you wanted to find this, the derivative, it would be the limit when x approaches a of f of x minus f of a and x minus a. Interestingly enough, there are different times where each one is more appropriate. So sometimes using one definition makes it easier to find the derivative, and sometimes using the other one makes it easier to find the derivative. What is the derivative? Well, graphically, the derivative represents the slope of a tangent line. And physically, what is the physical interpretation? What can I do with the derivative? It is the instantaneous rate of change. So the typical example is that if you're driving in a car, so if you're driving on the road and you want to find the speed, then the speed, to find the speed, the normal formula is distance divided by time. So you need to know point A and point B, like how far did you travel and the time that it took you to move from one point to another. However, using the derivative, we can find the speed even if you don't know point A and even if you don't have those 2 points. If I just give you a specific time, let's say that this was at 1 second and this was 5 seconds later. So if I tell you, like, I want to know the speed that you were going specifically 2 seconds after you departed, that would be an instantaneous rate of change. That would be the instantaneous speed. And that can only, so these, it is so nice that calculus expands all of the concepts of physics. So in physics, you learn about velocity, and by using the derivative, now you can find what we call the instantaneous velocity, which technically means that you can find it at any instant, any time that you think. You don't need to look at the initial point and the ending point. Just by looking at the derivative, you find the instantaneous derivative. And this applies to everything. So if you were filling a tank of water, or maybe your pool, let's say since it's the summer, you're filling out a pool and you want to know how long it's going to take, you need to know like how fast, how many liters and how many ounces of water, liquid water, you're getting um, into the into the pool. And so finding the derivative would actually tell you how fast you're doing that job. Okay, so the derivative is one of the most important concepts in calculus. And we have different rules to find the derivative. So for example, if you have a power, so a power function looks like x to the power n. In that case, the derivative is going to be n multiplying x to the n minus 1. So we always, a quick way of reminding this is the exponents comes down multiplying, and you subtract 1 to the original exponent. So for example, if I have x to the 10, the derivative of that would be 10 x to the power 9. So you bring the 10 multiplying and subtract 1 to the 10, which is 9. Now, if you have a combination of polynomials, of powers, you could apply the derivative individually to each one of them and then just add them or subtract them. Basically, you're using the same sign that they had originally. So if your initial function is 6x to the power 6, the derivative of this piece would bring down the 6 multiplying. So you'll have 6 times 6, which is 36, and then subtract 1, 5. Now, since there's a minus, your derivative is going to have a minus. 3 times 4, that is 12, and then subtract 1 to the exponent, x cubed. Here, bring down the 3, so this is 3, subtract 1 to the 3, so you get 3x squared. Now, interestingly enough, the derivative of x is actually just 1. Think about it, because if you subtract, let me do it here. If you had just x, which is x to the 1, and you apply the rule, you would get 1 times x to the 0. But any number to the 0 power is 1, so this is kind of like 1 times 1, which is 1. So the derivative of x is 1. But since you have this 3 multiplying, then your final answer will be like 3 times 1, which is 3 at the end. And last, the derivative of 9 is 0. So the derivative of any constant, a constant, it's something that doesn't have a variable. So for example, 3x is not a constant because the variable is right there. Even though you may say, oh, but 3 is a number. Yes, but the variable is multiplying. So the only constant that has no x's, no variables is 9. And so the derivative of 9 is 0. So I didn't write it, but I could have written an extra 0 there, which would be the derivative of that 9. And often we like to kind of like add funny constants, like not funny, but special constants, such as like if I had pi, the derivative of pi would be 0 as well, because pi is a number. Even though we use a letter to represent it, it represents a unique number. It doesn't change. It's something like 3.14. So keep that in mind. Sometimes we have these special letters that represent numbers, and so the derivative of those things, we treat it as if it was a constant. Okay, so another very common rule to find derivatives is actually the product rule. And an example would be x squared cosine of x. Very important, if you're going to use the product rule, identify that you have a multiplication. So this is a multiplication. Sometimes you don't need to apply the product rule. Sometimes you can simplify your multiplication and instead apply simply the power rule. But this is a case where there's no way to simplify. Cosine of x is a single function. It is not cosine times x. If you just write the cosine, it doesn't make sense. So in fact, the full way of writing cosine should be using parentheses, which does not indicate multiplication, but it indicates that this is the input of the cosine. So according to the rule, the derivative of a product or a multiplication is the derivative of the first times the second plus the first times the derivative of the second. So I start by breaking up the function into my first function, which is x squared, and my second function, which is cosine of x. Then I find the derivative of each one of them. The derivative of x squared is 2x. The derivative of cosine is negative sine. And if you substitute in the formula, you get, notice this is my formula. So it's going to be 2x times g, which is cosine, plus f, which is x squared, times the derivative of g, which is negative sine. And then at the end, we always like to simplify. Uh, Often when students, I see often students don't like writing many parentheses. Either the student forgets or you don't write it. But if you don't write the parentheses, it's more like you're saying x squared minus sine of x instead of multiplying them. And I've seen it where like sometimes the students tell me like, no, I know that they're multiplying, but then when I ask you to solve it, you forget later. So it's because it's confusing. So the simplification of that would be to put the negative on the left, kind of like move it to the left, put the x square and then the sign. So this multiplication gives you negative x squared sine x. So always is very important to learn to simplify. Another important rule to find derivatives is the quotient rule, and an example would be ln x over x cubed. Very important again, identify if you need to use the quotient rule or if you can simplify it while using the quotient rule. So in this case, the derivative of the natural log is 1 over x. The derivative of x cubed is 3x squared. And if you put everything, and the formula is kind of like similar, but there's a negative and there's also a g square. So if you remember, if you memorize the product rule, then the quotient rule just has a negative in the middle and has the whole g square fraction on the denominator. So do your substitution. F prime is 1 over x, g is x cubed, minus f, which is ln, times g prime, which is 3x squared. And careful here, just like the cosine of x, it's not a multiplication, it is cosine of x. Same thing with the logarithm functions. So I cannot actually distribute the x with the x square and get x cubed, because technically there's like a parenthesis around the x, and nothing goes into it and nothing comes out of it. So the simplification of this is usually putting the 3x squared on the left. So when you multiply them, you get 3x squared times ln x, or times ln x. On the left-hand side, you can actually simplify one of the x's. So the x in the denominator simplifies with one of the x's from x cubed, and you get x squared. And the simplification here, whenever you multiply, I call this a power of a power. You multiply the exponents, and this is x to the power 6. So this is one of those rules of exponents, which sometimes we write it like this. A to the power x to the exponent y. This is a to the x times y. So if you multiply 3 times 2, you get 6. Okay, another important rule and one of the headaches for students, this is the chain rule. The chain rule, it's basically when you have a composition of functions. So if we look at the example, we have a power. So there's a power, but then the base, instead of the base being simply x, the base has a whole expression, which is 1 minus 10x. So anytime that you have like those big expressions, it often indicates that there is a composition of functions. So the idea is identify the outer and the inner function. So the outer function would be eliminating everything that is inside the parentheses. So the whole parentheses becomes the letter u. So the inner function is 1 minus 10x. And notice that the outer function, I write it as 2u to the power 2026. Now you apply this formula. So you're going to find the derivative of the outer function. If you look at this, it's going to be a power rule. So the 226 comes down multiplying, you subtract 1 to the exponent, you get 2025. And then as you do your multiplication, you get 4052 u to the power 2025. Next, you find the derivative of the inner function or the inside function. The derivative of 1 is 0 minus the derivative of 10x, which is simply negative 10. And so the chain rule says that you find the derivative of the outer function and then times the derivative of the inner function. But the outer function has to be evaluated at u. So I got this for the derivative of the outer, so I gotta go substitute the u with the whole 1 minus 10x, and then times the derivative of the inner or the inside, which is negative 10. And in this simplification, because of the exponent, you can now multiply the negative 10 times anything that's inside the parentheses. However, you can multiply the negative 10 with the 4052 to get negative 40,520 power 1 minus 10x to the exponent 2025. So this is the final answer. And again, the way that you remember this is simply by saying that if you have a composition, you multiply by the derivative of the inside function or the inner function at the end. Because notice, otherwise I would have just had the power rule, but then I had to multiply by that negative 10. So this is a very important rule as well. So implicit differentiation is something that we use when y cannot be solved explicitly. So when you cannot isolate or y is not isolated. So an explicit function would be, for example, y equals x squared plus 3, because the y is explicitly defined as x squared plus 3. Or another example of an explicit function would be y equals the square root of x plus 1. However, sometimes we have times where the function y, it's implicit in the equation. An example of this would be x squared plus y squared equals 25. And a more complicated example is x cubed plus y cubed equals 6x plus y. Well, it is very easy to solve for y on the first equation, and easy in quotation marks. In the second equation is very complicated, almost impossible if you don't know like a lot of the techniques to like simplify and combine these things, which even when you know them, it could take you a lot of time just to solve for y in this equation. So this is one of those where we wouldn't want to solve for y. However, we can still find the derivative by using the implicit method. And the implicit method, basically, all you got to do is find the derivative on both sides of the equation with respect to x. However, since y represents a function, so remember that y is a function of x. So even though you see this equation, it's kind of like the previous one. So y is a function itself. So anytime that you do a derivative of y, you got to think of a chain rule because y, it's a whole function. So y depends on x. Let's look at an example. So an example where you would apply implicit differentiation would be this equation. And so I want to find the derivative, which you can represent as dy over dx. So you apply the derivative on each term on both sides of the equation. And anytime that you have a y, you're going to apply the chain rule. So for example, I have the derivative of x squared, that is just 2x. I have the derivative of y squared. Well, y squared would be 2y, and then times the derivative of the inside, and the inside function is y. So you multiply by the derivative of y, which we write as dy dx. Then minus one more time the derivative of y. Think of derivative of y's as derivatives of x. The derivative of x normally would be 1, so you get a 1. and then times the derivative of the inside function, which is dy dx. And then on the right hand side, you have the derivative is 4 xy. So since 4 is a constant, you could just factor out that 4 and multiply the whole derivative at the end by 4. And when you have xy, you apply the product rule on xy. So it would be, and I think I have it written backwards. The way that I would have done it is, so f would be x and then g would be y. So I would have find the derivative of x first, which is 1 times y plus the x function, the f function, times the derivative of y, which is dy dx. So notice that if you switch the order, you get the same thing, like x times dy dx plus y, because 1 times y is just y. And there was an x at the very end. The derivative of that x is just 1. Okay, so now that you have all of this, now you want to combine all of the y's on one side. So I'm going to distribute or expand this by multiplying by 4. So I get 4x dy dx times 4 times y, which is 4y. So that's all I did from this step to the second one. Now identify the dy dx. So here, here, and here. I want to have those three on one side of the equation and move everything on the other side. So sometimes we say collect or group the dy dx terms. So this becomes 2y dy dx minus dy dx minus 4x dy dx. So I move all of them on the left and everything else on the right. Now you can factor it out because all of those are multiplying. And notice that what you get is what it's inside the parentheses. So 2y, there's a 1 here, so -1, -4x, so it's there. And once you factor, since it's a multiplication and you want to find dy dx, then you just divide on both sides by the whole parentheses. And you get this divided by the whole parentheses, which is this. And that's my final answer. So that's how you find the derivative using the implicit differentiation method. Let me do then what are something else that you could do with the derivative? Well, a typical question for the derivative is to find the tangent line at a point, because the derivative represents the slope of the tangent line. So in this question, I would find the derivative of this, which is 3x squared minus 6. Then to find the slope, I plug in the number where they want me to find the tangent line. So I substitute x with 2, and this gives me 3 times 2 squared minus 6, which becomes 6 at the end. So the slope of the tangent line is 6. Next, you wanna use this formula, but to use this formula, you need to know the y-coordinates. So to find the y-coordinate when x equals 2, you substitute in the original function, and that gives you -2. And so then you substitute the y1, the m, which is the slope. It comes from the derivative, and the x1. Everything, the other y and the other x remains. And once you simplify, you find the equation of the tangent line, which is 6x minus 14. So one of the important things that we do in calculus is find what we call the critical numbers. These critical numbers are supposed to be numbers where the derivative is 0 or where it doesn't exist. And these numbers are possible locations for maximums and minimums. So this is an example of how to find critical numbers. You find the derivative, you factor it, set it equal to 0. And once you solve for each factor, I found 1 and 3. And so these are my critical numbers. Now, I don't know if it is a maximum or a minimum yet, but we're going to see that in the next example. So to find if something is a maximum or minimum, we use the first derivative test. So we're going to have a local maximum if the derivative changes sign from positive to negative, because it means that the derivative is increasing and then it becomes decreasing. In a similar way, if the derivative changes sign from negative to positive, then the derivative the graph has to go down and then up. So it makes that point to be a minimum. So a local minimum is a point where the derivative changes sign from negative to positive. And you could also have points that are not maximums or minimums. This is when the derivative doesn't change sign, and examples of graphs where when there's not a maximum or a minimum would be the little graphs that you see below. So in this same example, if I wanted to find the maximums and minimums, remember that I already had the critical points, which were 1 and 3. So next, I would create a sign chart for my derivative. So my critical numbers 1 and 3 become dividers. They split the entire line in 3 intervals, everything to the left, everything between 1 and 3, and everything to the right of 3. Then you pick one point, it doesn't matter which point, you pick one point inside each interval and substitute the derivative, substitute those points into the derivative, not the original graph. So 0 gave me 9 because it's positive, I put positive signs. 2 gave me -3, so I put negative signs. And 9 gave me 9 is positive, so I put positive signs. So by looking at this diagram, I know which one. So these changes, if I move left to right, this changes from positive sign to negative. So 1 is going to be a maximum. And 3 changes from negative to positive. So 3 is going to be a minimum. And so also the x intervals where the graph is decreasing or increasing. So since anytime where I get the derivative positive, the graph is increasing. So from negative infinity to 1 and from 3 to infinity is positive. And so I put this in my answer. And between these two critical numbers, between -1 and 3, the graph is decreasing. And my local maximum and local minimum are 1, 5, and 3, 1. So I'm nearing the end of the hour, so I'm gonna do probably one more problem. I'm gonna skip to the. There was one more question that I wanted to talk about before I do this. The optimization. So this is one of the typical applications for calculus in derivatives. So an optimization means that you want to find the optimal value. So for example, what is the largest area? If you have a rectangle with given measurements, like if you have certain amount of material that you can use to fence, what would be the dimensions that create the largest area? Another question is, if you have a box, what is the least amount of material in order to host the same volume, the same amount of volume? And in general, when you have costs, like if you have a business, you want to have the minimum amount of cost and maximize your profit. So anything that has to do with finding minimums and maximums is usually called an optimization problem. And so the typical process is draw or create a picture or a diagram, introduce variables, write the equations, rewrite the objective function using one variable, find the derivative, the critical points, and then verify which one is the minimum and the maximum. So for example, a farmer has 240 meters of fencing, wants to enclose a rectangular field, find the dimensions that maximize the enclosed area. Well, The dimensions that maximize the enclosed area. So I'm gonna introduce my variables. L is the length, W is the width. Because there's only 240 meters of fencing, so if I add all of the fencing that I'm gonna need, 2L plus 2W, that's equal to 240. I could divide by 2 to simplify the equation as L plus W equal 120. Then I can solve for W by moving the L on the other side. And my objective function is what I wanted to maximize or minimize. Since I want to find the largest area that I can create with these 240 meters of fencing, then my formula is going to be the area of a rectangle, which is L times width. But this has two variables, so I can now rewrite it by substituting the W. So if I substitute the W, I get L times 120 minus L, which becomes a quadratic equation. Now you can find the derivative, solve for set it equal to 0, and you find L equals 60, which means using 60 meters on the length, that will give you the highest. And then using the other equation, you could also find the width, which is also 60. And this is how I verify that indeed these numbers give me the maximum. So if you evaluate the second derivative at 60, it gives you -2. The second derivative test says that if the derivative is negative, if the second derivative is negative, that is a local maximum. So I know that I'm going to have the largest area, the maximum area possible when I choose a length of 60 and a width of 60. And this would be the area. Okay, well, I'm gonna stop here because it's almost gonna be 2 p.m. and this was supposed to be just like a 1 hour review. So I wish you good luck in your final exams. And if you have any questions, maybe we don't have a lot of time, but if you have any questions, feel free to post them on the chat and I'll answer your questions.
Thank you, Mr. Tintos. This is a great presentation. So does anyone have any questions for him? Well, again, thank you so much for the presentation and helping everyone get ready for their finals. And I'd like to thank everyone for coming into the Tejano virtual events today and supporting our workshops. Yes, the PowerPoint will be provided. If you go to the YouTube channel for EPCC, you'll see that there is a Tejano virtual events playlist, and you'll be able to find this video there, and you'll see the PowerPoint there. So yeah, you'll be able to view it. But again, thank you all for coming. We appreciate your support. I have put in the chat box the link to the Tejano Passport Program, which will give you points for attending today's event, as well as any events you go to that offer Tejano Passport points. So good luck on your upcoming finals, and I hope you all have a restful break before the fall semester begins. So take care.